Studying our Laplace transforms. What have we discovered so far? We discovered they're an integral transform. This integral here, this integral is the Laplace transform of the function little f of t. It's an integral that has a value, but of course the value that it's going to have depends on this quantity s. So the integral is a function of the new variable s. This is the Laplace transform. So you stick in a function little f of t, you get out of it a function which is the value of that integral. And it depends on the quantity s. Typically we denote this, sometimes we denote this with a capital F of s, or we want to indicate the process, we write script L, curly L of f, curly L of little f. Or sometimes, especially when you're working by hand, it's denoted quite minimally by simply a little f bar. Little f with a bar across the top of it. Okay. We took the time to establish several important properties of it. I'll remind you of the two most important ones. The two most important ones are the transform is linear. It's a linear transformation of a function. That comes just from the fact that integration is a linear operation. You integrate a combination like this, alpha f plus beta g, it is equal to alpha times the integral of f plus beta times the integral of g. Okay. Integration is linear. The Laplace transform is built using integration, so therefore it is linear. Now, the Laplace transform is going to be a method that we're going to use to study ODEs, ordinary differential equations. So of chief importance is how the Laplace transform behaves on derivatives of functions. This is the second key property, theorem 2.3. If we assume that the function little x has a Laplace transform, so if that integral, the integral of e to the minus st times little x of t dt, 0 to infinity, if that integral converges, so if the Laplace transform of little x converges for certain values of s, this property says the derivative of x will have a Laplace transform too. So that's nice. And it'll be related to the transform of x in a very specific way, described by this equation here. The Laplace transform of the derivative is s times the Laplace transform of the original function minus this constant, which is the initial value of x evaluated at t equals 0. We can iterate this result, apply it again and again to get the Laplace transforms of higher order derivatives. Now those properties are summarized on this two-page table of Laplace transforms. It's on pages, whatever it is, 42 and 43 of your notes. On the first part of it, we've got the transforms of lots of standard functions that we run into. Okay? All the various trigonometric functions, exponentials, polynomial, all these kind of functions, we have their Laplace transforms recorded here. And some of the basic, well, in particular, the basic property about how the Laplace transform behaves on derivatives is also summarized here. First derivative, second derivative, third derivative. Those are the ones we commonly see appearing in differential equations that come from applications in science. Okay? First, second, and third derivatives. So just finishing up on this summary, that led us to taking the transform, making use of the recorded results, making use of the properties, that led us to this method for solving ordinary differential equations. It was a four-step method, which fairly straightforward description of it. Achieving some of those steps might involve a bit of algebraic manipulation, a bit of usage of partial fraction expansions and so on. So using algebraic tools and algebraic working, you should be able to get through these four steps. And the first step, so we're solving an object like this, an ordinary differential equation like this, featuring the single unknown function y of t. Okay, we're solving it by first transforming the whole equation using the Laplace transform. And the Laplace transform at the left-hand side is going to be that combination of the individual Laplace transform. Each of the terms on the left-hand side is either the unknown function y or one of its derivatives. So we can apply the Laplace transform of derivatives property. That will introduce, and if we can, we transform the function g of t appearing on the right. Now, the transform of derivatives will introduce various constants, those initial values of x and its higher derivatives. Very often, those values are supplied to you as part of the specification of the problem, because typically we're modeling some kind of system, and its state is known at the beginning of time, and the differential equation describes its evolution over time. So very often we know the starting values from the mathematical model. So we insert those conditions where we have them, simplify the equation as much as we can, and then we solve it for the unknown transform y bar. If you solve the transformed equation, so you get an expression for y bar as some kind of function of s, typically some kind of rational function, ratio of polynomials, or some kind of combination of those functions. And then the final step is just simply, well, simply in quotes, to take the inverse transform. That you may or may not be able to do that immediately with the help of the table, or you might have to do, and we've seen it in some of the examples, various preparation steps to kind of rescale the functions you're looking at, take out factors to get them to match functions on the table, or take partial fraction expansions so that the complex rational functions are expressed as simpler ones, and the simpler ones can be found in the table. And then making use of the linearity property as well. So the inverse transform of a big linear combination of different functions, we can take the inverse transform of each one and take the appropriate linear combination of the results. So that work occupied us in the last couple of weeks. We were able to extend it without too much trouble. I always get drawn into long summaries. Anyway, but it's good to revisit these things. We were able to extend it without too much trouble to simultaneous ODEs. In principle, any number of ODEs featuring that number of unknown functions, where they're all kind of mixed up, and the equations typically feature multiple of the unknown functions. Okay, in practice, we only just looked at situations where we had pairs of functions. So this was an example where we had two unknown functions, x and y, both functions of t. And the equations are coupled. That's the descriptive term for when both of the functions appear in both of the equations. So it's not like you have one equation for x, one equation for y, and you could solve them separately on their own. Both equations refer to both the unknown functions. They have to be solved in that kind of simultaneous way. But the four-step method we've just been looking at applied equally well to those kind of systems. Okay? Transform both equations, solve simultaneously using the principle of elimination, solve the transformed equations for x for the transforms of x and y, and then in principle take the inverse transforms at the end to recover the solutions x of t and y of t of the original problem. So any queries or questions that you might have at the moment, just on that overall summary or on the four-step process? Is there any burning question anyone has at the moment? So what you should make sure you've been doing, and if you haven't done so, do make sure you do it, is get some good practice at solving differential equations and at solving pairs of differential equations. There's a number of examples in the tutorial exercises there. If you look at the past exam papers on Moodle, you'll find examples where this kind of question has been asked in exams, and we will do further practice with those in revision sessions and demonstration sessions here later in the term. But it is a very important skill in this chapter, and it's the kind of central kind of thing we're trying to teach you to do in this chapter. Okay? So you should be well practiced at taking a differential equation and its initial conditions and going through that whole four-step process and arriving at the solution. Okay. So we've got a little bit of further work to do with it. And that further work is going to be about extending our range of functions that we're able to deal with. Okay. So at the moment, when you look at the table of transforms, you've got a whole load of familiar functions, trigonometrics, exponentials, polynomial type terms down the left-hand side. We want to slightly widen that out now. I mean, we're motivated to do this from I mean, this is an example of a differential equation. Well, it features an integral, so you might call it an integral equation as well. But equations featuring, so here, the quantity I of t is the current flowing through this circuit at time t. Now, we're not going to suddenly dive into the theory of electronics and so on, but I just want to pick out just a feature of this kind of example. So we're not trying to understand the details of what's going on here, okay? But from physics, from electrical engineering, there is a theory of how the current flowing through the circuit is described, and it's described because you've got a number of things here. You've got a resistor, and this might be some kind of light element, and a C, that symbol up there is for a capacitor, an electrical component that charges up and releases its charge in some kind of way. And the behavior of all that is governed by this differential equation. The thing driving the circuit is this power source up here, which is an alternating current, because you see it's got this sine omega t. Omega is that W-like Greek symbol. Omega is a frequency term, so that sine of t will be this oscillating signal, and that's what's representing the alternating current that's driving the circuit. You have this familiar idea. Alternating current is constantly switching back and forward many, many times a second. What's the typical frequency of the stuff in the wall coming out from plugs? 2. Anybody know? Something hurts. It's something like it's multiple times a second, probably a couple of hundred times a second. The direction of the current is changing. It's a very fastly oscillating thing. Anyway. So, but a fundamental part of that circuit as well is this symbol up here in the top left, which is a switch. See, there's a break in the circuit there. So that's the kind of circuit drawing symbol for a switch. So that can be open and closed. So if you think about what the kind of graph of the current coming out of the power source in this circuit might be, you know, the thing might be switched off. So there'll be no power coming from the power source, no current. But then at some point it's switched on, and so this alternating current from the power source is switched on. And then at another time it might be switched off again. So we've got this kind of function of time, and we somehow want to represent the idea of something being switched on and switched off. Okay, so there's an interesting interval here where there's stuff happening from the power source, but then outside the interval, the thing is switched off. So we want to bring into the discussion, which will be helpful for some of the applications, we want to bring in the idea of a switching function. Okay? A switching function, a function that can do the job of switching various functions or signals or inputs, switching them on and off. Okay? So that's what we're going to do now. So we're going to look at enlarging what we're going to say? Enlarging the landscape of functions that we can see in our ODEs. Okay. So a switching function. Okay, so this has a name. This is named the Heaviside step function. So it's a function we want to introduce which embodies or does the job of doing a switch. And you'll see it in a moment now. It's got a very simple definition in some ways, but it's surprisingly flexible when we allow ourselves to take linear combinations of it. Okay, this is the Heaviside step function, h of t. Here's the definition of the symbol of the function. Well, it takes only 2 values, either the value 0 or the value 1. We're going to say it takes the value 0 for every time input less than 0, and it's going to take the value 1 for every time 0 and beyond. Which one you make the less than or equal and which one you make the strictly greater than isn't really so important. But just the switch happens at t equals 0. Yeah? At all negative values of t, the thing is switched off. Negative value 0, that's nothing, the absence of something. And at t equals 0, it switches on. It suddenly takes the value 1. So it's certainly not a continuous function. It's got a discontinuity at 0. And it's got a pleasing enough graph. I mean, it's equal to 0. I'll draw it down here, all along here. And then suddenly here it jumps up to the value 1. And that kind of behavior continues in both directions. Okay. So it's not a completely boring function. A completely boring function would be 0 everywhere. Moderately exciting. It's 0 everywhere negative, and then it suddenly switches on and takes the value 1. Okay, now, is that enough? Is that single function enough to do lots of switching on and off at various different times? Well, yeah, it is, because notice what happens. Notice what happens when we shift the argument. Well, what do I mean by shift the argument? Well, think about the function h of t minus a. So when a is some real number, and I don't look at the function h of t, I look at the function h of t minus a. Well, there's only two possible values this function can take. It's still a 0, 1 function. That's all the function h does. It's either 0 or it's 1. So that's going to be the same for h of t minus a as well, because it is fundamentally the function h. You can't do anything else but take the value 0, 1. The only question is where the switch happens. Yeah. And the original definition was that it was 0 whenever the argument t was negative. So that's still the case here, whenever t minus a is negative. And it's going to be 1 whenever t minus a is non-negative. So in other words, i.e., this is when t is less than a, and when t is greater than or equal to a. So the effect, of course, of shifting the argument like this is just to shift the location where the switch happens. Yeah, seems quite straightforward. Assuming a is a positive number, then the change in behavior happens at a. Great. So that's good. We don't need a whole load of separate functions, really, to change the position of our switching. We just need to, we can make use of this single function h, but just shift the input to it. Okay. Now, but let's investigate this a little bit. So we've got two examples here in example 2.11. If we let a be less than b, what does this function g of t do? So g of t is this combination, h of t minus a minus h of t minus b. So I'm taking a linear combination of two shifted variants of the h of the Heaviside function. Yeah, shifting the first one by a, and then looking at the difference between the other one, which is shifted by b. Okay, well, what possible values could g take? Well, see, each of these bits here is at any particular time is either going to be 0 or 1. So the range of values that g could take would be maybe, 0, 1, or 0 or 1, really, or maybe minus 1. Because these bits are only 0 and 1. If you're looking at the difference between them, it's either going to be 0, 1, or minus 1. But let's think about it carefully and see what happens. I mean, the easiest way to think about it is by drawing a graph. I mean, we will assume for the sake of argument that both of them are strictly bigger than 0, just so I can place the vertical axis somewhere. Here's t, here's g of t. So what's happening? Well, remember, think of this new definition we have. So the shifted Heaviside does its switching from off to on at the location which is equal to the shift that you subtracted. So when t is very negative, and when t is less than a, neither function is switched on yet. Okay. So at the values of t before a, neither function is switched on, so the value is 0. But when t passes the value a, this first one gets switched on. Yeah. This first one takes the value 1 at every point beyond a. The second function is still switched off because t hasn't reached b yet. Okay, t is still less than b. This second function switches on at b. So 1 will be somewhere here. So the function takes the value 1, jumps to the value 1 as it passes through a. And it continues to take the value 1 until it passes through b. And when it passes through b, the behavior of the second term, h of t minus b, changes. That gets switched on, this second term, because it switches on when t passes b. But when it switches on, it takes the value 1, but then g of t is going to be 1 minus 1. So the effect of that is going to be something like this. Okay. So, I mean, that's pretty much a proof. You don't really need, not losing anything by avoiding it, the formality of it. G of t is going to be 1 if a is less than or equal to t, is strictly less than b, and it's going to be 0 otherwise. So it's switched on in the interval a to b, it's switched off otherwise, for t outside of that interval. Is that clear? Everybody see that? When you take these simple linear combinations, these differences of two Heavisides like that, you get a signal or an input that's switched on in a certain interval and switched off otherwise. The second example just extends that slightly. What does this function look like? So 1 plus cosine of t. And that's multiplied by what we had before, h of t minus a minus h of t minus b. We're still assuming that a is less than b. Well, what happens here? Again, best illustrated with a graph. And these are examples, but they are examples that pretty much represent some general behavior. So, like, what does the function, I mean, if you ignore the combination of Heavisides, just think about the function 1 plus cosine of t. Well, what does that do? Well, that takes an average value of 1, and the cosine part oscillates between 0 and 1. Yeah? So whatever it is, it's some kind of oscillating signal between 2 and 0. I'm just putting it in a dotted way for the moment. So it's a cosine function shifted up by 1. You introduce that shift there on the value. But of course, it's not just that. If it was just that, then that would be the graph of it. But it's multiplied by this. And this is a factor. It's a switch. Yeah, multiplying by that combination of Heavisides is a switch. And it switches whatever it's multiplying on between A and B, but leaves it switched off otherwise, because it multiplies it by 0. It kills it. So the graph of our function f of t there is, well, this solid line part. Just being vague about how these stand with regard to the multiples of pi or whatever, which part of the cosine cycle we're at. I don't care. But I'm just trying to indicate the fact that if you've got some kind of signal, multiplying it by this difference of Heaviside switches it on and off at the values a and b respectively. Yeah? Switches it on at a and then switches it off at b. Because it's a multiplying factor, which is either 0 or 1. It's 1 inside the interval, 0 outside. So now you can see that just that single function h is starting to look quite versatile. Now, it can switch, it can be used as a multiplying factor to switch any signal on and off in any desired interval, just by choosing the values a and b appropriately and multiplying it by whatever the desired input signal is. Okay. So that's our function f of t in the red there, the solid line. 0, 0 outside the interval. And it's even, it's even more of a, it's even more versatile. The question 3 says, consider the function v shown here. V is a kind of a function that switches on. V is some kind of function that switches on in maybe a bit more of a controlled way. It doesn't just immediately switch on like that. Sometimes you want to be careful about switching on complicated machinery. Maybe you want to increase the power slowly. So v of t is presented to us in a case-wise definition here. So it's either 0, t, or 2. 0 for t less than 0. T for between 0 and 2. And it's 2 for t greater than or equal to 2. So it's this kind of ramp function. It's switched off, then there's a kind of an increasing ramp up to a certain level, and then it's at the value 2. Agreed? That's pretty much the function v. This value here where it levels off is 2. Now, okay, what's the point? Is there a way that we can represent v with Heaviside functions? So rather, we want to, that's a perfectly good definition of v. It's kind of case-wise definition. It's this value if t looks like this, if t looks like that, or if t looks like the other possibility, it looks like that. But kind of different cases of input argument t. But what the Heaviside step function allows us to do is to represent it using a combination of Heavisides. Okay. So how can we think about this? Well, you just want to look at the various component parts and think about how they all go together to make up the function v. So how can we express v of t? Well, v of t, we don't have to worry too much about the negative values, but between 0 and 2, it's equal to the value t. So we just use our previous example. I automatically did a full stop there. Let's cross out that full stop. So I'm not finished. But this bit, the ramp bit, is represented by this combination of Heavisides. Because it's the signal t, so that's in the graph y equals t, the infinite 45-degree line. But we just want to pick out this little bit of it between 0 and 2. Yeah? The function t continues on in both directions, according to that dotted line, but the part of it that's in v is just the bit between 0 and 2. So we have the input signal t switched on between 0 and 2. But then something new happens at 2. When you get to the value 2, the constant function 2 takes over. Okay? So when we get to t equals 2, this term will be switched off again. So we just have to generate v on the values of t greater than or equal to 2. So I can do that with plus 2 times h of t minus 2. Now full stop. Now that equation is true. So this combination of Heavisides has the effect of reproducing this function b. For negative values of t, none of the Heavisides are switched on, so it's just 0 plus 0 plus 0. For values of t between 0 and 2, the h of t minus 2 is switched off. So the only part that gets generated is t. That generates the round. But when we get to t equals 2, this part switches on, which has the effect of killing the function t, because now it's in the bracket, it's 1 minus 1, 0. But this one switches on, which switches on the constant function 2. So that maintains the graph at that level 2 for all future time. And this, we've got the same Heaviside function appearing in a couple of places here. So, we could re-express this as a linear combination t times h of t plus, or minus, let's say, minus t minus 2 times h of t minus 2. Okay. Now, we haven't really achieved that much, really. It's just a nice way of re-expressing things. But what it does allow us to do is get away from this case-by-case type definition. And it takes a function which is piecewise, defined in various pieces, and with the use of this single switching function, h, the Heaviside function, allows us to get a more conventional expression for the function as a combination of various versions of the Heaviside function. Now, second function, so I said this was about enlarging the landscape of enlarging the landscape of functions. The second function we want to introduce is the Dirac delta function. Paul Dirac was a mathematical physicist who was involved in development of quantum mechanics in the last century. So this function is named after him. It's strictly, technically speaking, not a function, because it takes the value infinity. But it's still called a function. That's the name attached to it. So strictly not a function in the conventional sense. It's more like a distribution. Those of you doing statistics and probability, you have probability density functions, and you never really evaluate them at single values. It's irrelevant what particular values they take at any one single point. What's more interesting is how their integrals behave, how the functions distribute probability over intervals when you're talking about a continuous random variable. Continuous random variable, you don't so much speak about what precise value it has. You're rather more interested in judging what range is it in, or what interval of values does it occur in. So a distribution is a kind of mathematical object that we're only really interested in it for its intervals. And that's kind of what the Dirac delta function is really. But to just accept it for the moment and use the word function, it's fairly quick to describe. And it's quite exciting. Well, most of the time it's boring. It takes 0 at every value of t, except at t equals 0. I mean, how much more exciting could it be? It takes a value infinity. Okay. I mean, you can't really draw a graph of it. You can kind of attempt to draw a graph of it by indicating it's 0 everywhere. And at the value, at the input value t equals 0, it's, we can't really draw it. Just point upwards, takes a value infinity. So this can be like in physics, and when you get into differential equations or modeling physical systems, this can be used to model the delivery of shock inputs to systems. some kind of explosive effect, which for modeling purposes is treated as if it just happens instantaneously at a single point in time, rather than some effect which is more conventionally distributed over a certain interval of time. So something like an explosion or a shock delivery of some input into a system, okay, which in the model is modeled as happening instantaneously. That's the Dirac delta function. So it's got this spike, shoots up at the value 0. And similarly, we can shift its arguments. So similarly, like the Heaviside, shifting the argument shifts the spike, shifts the location of the spike. So delta of t minus a, boring everywhere, except at t equals a. T equals a, it delivers the value infinity. So what we would like to be able to do is to be able to treat differential equations that feature some of these functions, to treat them in the same way we've been treating the differential equations up to now. So we would like to admit them into this 4-step process, being able to transform the equation, solve the equation for the transform variable, and then take inverse transforms. We would like to be able to do that for differential equations that feature these functions, or might feature these functions in their solutions. So what do we have to be able to do in order to do that? Well, we have to know what their Laplace transforms are. Okay. So what are their transforms? And if we're going to be able to solve ODEs that feature these in the original ODE, we need to be able to apply the Laplace transform to one of these. So a basic question is theorem 2.4. Theorem 2.4, which addresses the Laplace transform of just one of the Heavisides on their own, but we do it in general. We treat the shifted anywhere version. So we're going to assume additionally, this isn't quite in the notes, but this should probably be added into the notes. We'll assume the shift is positive. And generally, when we're looking at these applications, we tend to think of t as the time variable starting from some starting point 0 and going on. So we'll assume a is bigger than 0. What is the Laplace transform of h of t minus a? Well, the theorem says it's e to the minus as over s. Fairly well behaved. An exponential featuring the shift value divided by s. So not too bad, not too complicated. But, you know, we shouldn't just believe it because I said it. We should see a proof of it. I mean, it's not really proof. It's, well, you know, it's an application of the definition of the Laplace transform. I mean, what is the Laplace transform of h of t minus a? It's this integral. The integral of the exponential multiplied by the function. Okay, so we kind of need to know what the integral of the Heaviside function is. Well, except we don't treat it like that. We just remember, you know, really h is extremely simple, remember? It only takes the value 0 or 1. And really, the interesting things happen at a, so we should separately break the integral up like this, perhaps. And we can do that with integrals. We can break the integral from 0 to infinity. We can break it apart at an intermediate point a. That's just a basic property of integration. Okay, splitting the interval of integration. But see, now these integrals simplify, don't they? Because if we're at values of t between 0 and a, the Heaviside function hasn't switched on yet. So all we're doing here is just integrating 0 dt. Yeah, so the Heaviside step function is 0 on these values of t. So suddenly that integral is easy to do. 0. You're integrating 0, it's 0. This integral simplifies because for all values of t greater than a, you're integrating here from a to infinity. Well, for all those values of t, h of t minus a is equal to 1. So it simplifies to the integral of e to the minus st. So that's by the definition of h. Yeah. This version of it, because it's only evaluated between 0 and a, is 0. This version, because it's only evaluated at a, values of t greater than a, has to be 1. So the integral is just the integral of the exponential, which is, of course, e to the minus st over minus s, evaluated at t equals a, and taking the limit as t goes to infinity. Like we said, like in previous analyses, as long as the value the value of the real part of s is positive, this exponential e to the minus st, it's going to be e to the something negative, and the t is getting larger and larger, so it's getting larger and larger in the negative direction. So it's going to be converging to 0. It's going to be 0 minus the evaluation of t equals a, which is 1 over yeah. I just had a moment of doubt. I think I said evaluate at t equals 0. No, it's not t equals 0, it's t equals a. A is the lower limit. So what does this evaluate to when t is equal to a? We just simply substitute in t equals a. So it's e to the minus sa over minus s. So yeah, in total it's e to the minus sa over s. Two minus signs cancel. So we know what the Laplace transform of the Heaviside step function is. So that's our quick introduction to Dirac delta function and the Heaviside step function. You'll see there's a few further results to do. Theorem 2.5. Theorem 2.5 describes how the Laplace transform of a function multiplied by a Heaviside behaves, as long as we've got the same shifted argument in both parts. And theorem 2.6 is the Laplace transform of one of the Dirac delta functions. Okay, so what I suggest you do in advance of the tutorials, or in preparation for next time, is, okay, so we don't have the proofs of these results in this book, but just accepting these results, can you then go on to solve some ODEs featuring these equations? And it's the same, such as this example 2.13. It's the same four-step process, just bringing in and using these new properties of the transform that we have there. Okay. So we'll do further work with this at the lectures next week. I believe it's Stephen this evening, isn't it? For his classes. Yeah. Okay. Thanks for your attention.